All right, so let's go through the magnetic field of a solenoid. So the main purpose of this is I'm just going to highlight some of the key components of a solenoid and how we can think about them, since we are going to see them several times throughout this class. So you have a solenoid. It would have N loops around it. It would be some length L, and you would have current I going through it, and it would have some radius R. Maybe I can go in. There we go. Some radius R. All right. The magnetic field is nearly uniform along the axes, far from the ends. And a solenoid is longer than the radius. All right, so if we take our normal approach to looking at fields, we need to look at the contribution from one piece of the solenoid. So we have a solenoid of length L made up of N circular loops, and they're wound very tightly, so you don't have gaps like I drew here. So if we divide it down the middle, we would have Z, and we'd be looking at little chunks of delta Z. We would have our observation location, A, be some distance D from the center, and then you would have D minus Z to A, and L over 2 would be on this side, and L over 2 would be on that side. All right, so we want to think about how to approach each one of those loops getting summed together. So moving on, you have the origin, which is at the center of the solenoid, and the location of one piece is given in Z distance from the loop to the observation. A. So D minus Z, each loop contributes the same amount. So you may be asking, how do we go after the number of loops so this is generalizable? So how many loops in delta Z? Or number of loops. So you have N over L I think that has run out of ink. So N over L loops per meter. So loops in delta Z, N over L times delta Z. All right, so delta BZ is equal to mu naught over 4 pi 2 pi r squared I over d minus z squared plus r squared to the 3/2 n over L delta z. All right, so now we've got our expression for each little piece. And for step 3, we want to add them up. So b sub z is equal to delta bz, which is equal to the sum from mu naught over 4 pi, 2 pi r squared I n over L, delta z over d minus z squared plus r squared to the 3/2. And so we have bz is equal to mu naught over 4 pi, 2 pi r squared I n over L, some delta z, d minus z squared minus r squared to the 3/2. b sub z is equal to mu naught over 4 pi, 2 pi r squared I n over L, from minus L over 2 to plus L over 2, dz over d minus z squared plus r squared to the 3/2. Now, to solve this integral requires both substitution by parts so that you can get it into a format that you can use a table of integrals for. We're not going to do that. I'll just give you the solution. b sub z is equal to mu naught over 4 pi, 2 pi I n over L, from d plus L over 2 over d plus L over 2 squared plus r squared minus d minus L over 2 d minus L over 2 squared plus r squared. And typically you're looking at a distance far away, or d is the distance from the solenoid. And in the most typical case where r is much, much bigger than L, or sorry, the reverse, r is much, much smaller than L, b sub z is equal to mu naught ni over L. And we'll also study this result again in chapter 21, where we will look at a different derivation of this.